Hello and welcome to Transforming Your Company's Data Analytics, Championing the Digital Enterprise Certification Program. We're in our third course, Making Evidence-Based Strategic Decisions, and in week 2 we're looking at data-enabled decision-making. So in our fourth module, we're going to take a look at decision-making with incomplete and ambiguous data.
In this module, I'm going to introduce you to two types of statistics. There's frequentist statistics and there's Bayesian statistics. And frequentist statistics is what you probably studied in school. It deals with large data sets. And with these data sets, you apply different statistical tests to look for statistical significance. So for example, if you have a new vaccine and you want to say if it's effective or not, you would basically go out there and test the vaccine on lots of folks, collect the data, get a large enough data set, and then you would run some statistical tests to see if the effectiveness of that vaccine is actually because of what is in it, or is it just random chance? So first of all, how large of a data set do you need? Well, it depends on the population that you're trying to study. And in some cases here, you can study the entire population. In other cases, though, trying to study the entire population is going to take too much time and effort. So you can do some sampling. So for example, when I worked at the U.S. Patent and Trademark Office, I would do an annual training needs assessment. What were the training needs of our 13,000 plus employees? Now, to survey all 13,000 employees would take too much time, too much effort. So what I relied upon was sampling. So I would go out and randomly select folks from the population. And according to, and you can look at these tables, they're on the back of all the statistical textbooks, I needed 374 people at least to adequately represent the 13,000 employees. So with the 374 people or more, I can rest confident when I run those statistical tests that I had enough people that I can extrapolate from the sample results to what the population would do as a whole. So that's the idea here with frequentist statistics. You need a large data set, and you can kind of reduce it down to the sample size, but you still need a lot of data to work with. And the reason why is because we're working with something called the p-score. And this tells you, again, is it random chance or is there actual cause and effect here? So you can see here on the right, we have the familiar bell-shaped curve. And with statistics, we start off with a null hypothesis. And the idea here again is when we talked about the vaccine, we go with the hypothesis that the vaccine doesn't really have an effect. It's just random chance here. And if we want to say we are confident that the vaccine actually has an effect and will work, we calculate the p-score. And often we set the p-score to be 95% probability. And the idea here is if it's above the 95% probability that it's the null hypothesis, then we can say, yes, the vaccine does work because our p-score is less than 0.05. And that says that it's not random chance that this is working. It's an actual cause and effect relationship. Now, where you get in trouble sometimes is when we set that 0.5. What if you get a p-score of 0.51? Do you go ahead and reject that vaccine? Or what if you get a 0.0499 result? Do you accept that the vaccine actually has cause and effect? So you're right there on the fence there. And in some cases, you may want to rerun this again and maybe run some more tests to see if you can see a pattern on the p-scores. So that's one dilemma with frequentist statistics, the p-score issue when it's really close. Another issue is what do you do if you don't have enough data? If you don't have the large enough data set and enough information to make it statistically significant when you run those tests, how do you still make a decision? To explore that question about what to do when you have incomplete or ambiguous data or not enough data to use frequentist statistics, let's talk about a classic historical case study. In May of 1968, U.S. Navy submarine USS Scorpion sank off the Spanish coast. And rescue efforts were sent out, and people were trying to find the lost submarine. And the issue here is that submarine sinkings were pretty rare. Not many submarines sank, and it was difficult to try to find the submarine. They were using sonar, they were using last reported sightings, and the Navy, one of the Navy admirals had this idea of using a grid of squares and using Bayesian statistics to help do the search pattern. So they laid a grid over the ocean floor near the Spanish coast, and they used Bayesian statistics to help them find the submarine. So they calculated at the beginning what was the probability that the submarine was in that certain grid. And as they searched these grids, they would update the probabilities. And this is a key part of Bayesian statistics here. And one thing they also did is they went out and they surveyed experienced Navy commanders on various sinking scenarios, on what they think might have caused a submarine to sink. And they aggregated all these different scenarios and they fed that into the Bayesian formula, which helped basically recalibrate the hypothesis here, recalibrate the probabilities associated with each of the grids. And as we said here, the hypotheses were given conditional probability scores, and as the search teams checked each grid and found that the submarine was not there, they would update it, and that would affect the probability of the other squares that were not searched yet. So they did find the USS Scorpion using this system in October of 1968. And the issue what happened is that the USS Scorpion had a problem with its engines, and it sank to what they call the crush depth and basically imploded underwater. And they did find the wreckage scattered around those grids. And interesting thing about the grids is that these were in the high probability area. So this shows that Bayesian statistics can help you when you have incomplete and ambiguous data. What makes Bayesian statistics so powerful is Bayes' theorem. And the idea behind Bayes' theorem is that you can use degrees of belief. So if you're confronting a situation and you're not sure what the probability is, you can just assign a probability and then start looking at, okay, we calculate this maybe 50% guess, or maybe based on previous outcomes. And as we get more information, we can feed that back into the formula and further refine the probability that something's going to happen here. So a classic example I like to give the folks is, let's say you're playing poker, okay? And you're trying to guess who has what cards, your poker partners. And as you watch as people lay down cards and ask for new cards, you may start off with a 50% guess on each partner, but as you watch folks and as you see the cards that they're laying down and the cards they're asking for, you can further refine those probabilities to help you come to maybe this person has a straight, maybe this person has a full house, and you can start calculating the probabilities in your head using this Bayesian theorem. So as you gather more information and it's coming in, it helps you refine the probabilities and get you closer to the true value. And one of the really powerful things about Bayesian theory and Bayesian statistics is you can chain it together. So you can use this Bayesian networks. So let's say you're watching a baseball game, an American baseball game, and you're calculating, well, what's the chance the person will hit the ball? So we have a conditional probability on that. And then we say, okay, now, based on that, what's the chance they'll make it to the first base? And then based on that, what's the chance they'll make it to the second base? And you have a whole chain of probabilities here. It's all networked together. And it can help you figure out the final conclusion of what is the probability they're going to make it to home and have a home run. And that is the power of Bayesian networks here. It can help you deal with incomplete and ambiguous data. So as you're doing your data analysis, you're building up what you think is going to happen, the conditional probabilities based on more information coming into you. So you can start with a hypothesis and continually test it using the Bayes' theorem to achieve what you think is achieve what is going to be the true probability of this event occurring.
I hope you've enjoyed Module 4 and learning some techniques to work around incomplete and ambiguous data to help you make good decisions.